Imagine looking up at the night sky and spotting a galaxy that, against all logic, is growing younger instead of older. A cosmic Benjamin button spinning through the void, defying the relentless march of time. This isn't a scene from a science fiction novel or a distant fantasy. It's a real, documented phenomenon happening right now in the depths of our universe, and it challenges one of the most fundamental assumptions we have about existence, that time only flows in one direction. For centuries, we've understood aging as an irreversible process, something that affects stars, planets, and people alike. But what if the universe itself is capable of bending its own rules? What if some corners of space are not just evolving, but actually reversing their own clocks? Today, we're setting off on a journey to explore one of the most breathtaking mysteries in modern astronomy: why some galaxies appear to age backwards, and what this astonishing behavior reveals about time, reality, and the very fabric of the cosmos. We'll travel from the pioneering observations of the Hubble Space Telescope, which first glimpsed these rebellious galaxies, to the supercomputer simulations that are now helping us decode their secrets. Along the way, we'll see how these cosmic anomalies are forcing scientists to rethink long-standing theories, not only in astrophysics but in philosophy and fundamental physics as well. This is more than a story about distant stars and swirling nebulae. It's an invitation to reconsider what we know about beginnings and endings, order and chaos, and the arrow of time itself. By the end of our exploration, you won't just see the night sky differently. You'll understand why these galactic rejuvenations are more than curiosities. They're clues pointing toward a deeper, more dynamic universe, one where time is not a fixed river but a flexible dimension, full of surprises and possibilities we are only beginning to grasp. So let's begin. Think of a galaxy not as a static painting in the sky, but as a living, breathing entity with its own life story. This story begins with a colossal cloud of primordial gas, mostly hydrogen and helium, laced with the mysterious, invisible presence of dark matter. Under the relentless pull of its own gravity, this vast cloud begins to collapse, fragmenting into denser knots. Within these knots, pressure and temperature soar to unimaginable heights, triggering the nuclear fusion that ignites the first generation of stars. These are the brilliant, blue, massive stars that flood their cosmic cradle with light and energy, the vibrant newborns of the galaxy. But these massive stars live fast and die young. In a spectacular finale that can outshine an entire galaxy, they explode as supernova, seeding the surrounding gas with the heavy elements forged in their cores, the carbon, oxygen, iron, and all the other building blocks of planets and, ultimately, life. This enriched gas then cools and collapses again, giving rise to new generations of stars. This cycle continues, but with a crucial shift. Each successive generation of stars tends to be smaller, longer-lived, and redder. The furious pace of star formation begins to slow as the galactic gas reservoir is either used up, locked away in long-lived stars, or blown into deep space by the very stellar winds and supernova explosions that once enabled its creation. Over billions of years, the galaxy's vibrant blue hue, a sign of youthful vigor, gradually fades to a reddish glow. The massive blue stars are gone, and only the older, cooler, redder stars remain. Star formation sputters to a near halt. The galaxy has entered its golden years, becoming what astronomers call red and dead, a quiet, elderly structure where little new happens. Its evolutionary tale seems to have reached a predictable and quiet conclusion. This life cycle, from a chaotic, gas-rich youth to a stable, star-dominated old age is the standard model of galactic evolution. It's a narrative we've built from observing countless galaxies across the universe, and it forms the foundational backdrop against which every anomaly is measured. It is the rule that makes the exception so utterly captivating. For decades, the standard model of galactic aging seemed unshakable, a predictable cosmic life story written in the light of countless stars. But then, the Hubble Space Telescope began to peer deeper into the universe than ever before, and it started to send back data that didn't just add to the story, it threatened to rewrite entire chapters. Orbiting high above the distortions of Earth's atmosphere, Hubble's crystal-clear vision allowed astronomers to see the fine details of distant galaxies with unprecedented clarity. They expected to find a universe full of galaxies neatly following the rules, growing steadily redder and quieter with time. Instead, they began to find rebels. Hubble's images revealed galaxies that were, in a word, confusing. A massive elliptical galaxy, for instance, which should have been a homogeneous sphere of ancient red stars, would instead show a brilliant blue ring around its core, a telltale sign of recent massive star birth. In other cases, the spiral arms of a galaxy expected to be slowing down were instead dotted with the intense blue-white glow of stellar nurseries, regions where thousands of new stars were igniting in a furious burst of activity. These weren't just a few oddballs, they were a pattern, a systematic anomaly that challenged the very core of astrophysical theory. The data suggested that in certain pockets of the universe, the aging process wasn't just slowing down, it was being thrown into reverse. The most exhilarating and puzzling finds were often in galaxy clusters, the dense cities of the cosmos. Here, where interactions are frequent and violent, Hubble spotted galaxies that looked like they had been given a second youth. The telescope's sensitive instruments, like the advanced camera for surveys, allowed scientists to not just see this blue light but to analyze it through spectroscopy. By breaking the light into its constituent colors, they could measure the specific signatures of different elements and determine the precise ages of the stars. This was the smoking gun. The data confirmed that these blue regions were indeed composed of stars that were significantly younger than the rest of the galaxy, millions of years old, not billions. It was as if these galaxies had discovered a cosmic fountain of youth, restarting their star-forming engines long after they were supposed to have run out of fuel. This left the astronomical community in a state of thrilled bewilderment. The prevailing models had no easy explanation for this. How could a galaxy that had presumably exhausted its gas supply suddenly start manufacturing new stars? What mechanism could trigger such a widespread and localized rejuvenation? Hubble's surprising observations didn't provide the answers, but they brilliantly and undeniably framed the questions. They proved that our universe is far more dynamic and unpredictable than we had imagined, setting the stage for a frantic and fascinating scientific detective hunt to understand the forces that can make a galaxy age backwards. So what does it actually mean to say a galaxy is aging backwards? It's a phrase that immediately conjures up images of time reversing, of stars unliving their lives and gas clouds reassembling, a cosmic rewind button. But the reality, while less fantastical, is no less profound. In astronomy, backwards aging is a descriptive term, a shorthand for a phenomenon that defies our standard expectations. It doesn't mean the laws of physics have broken down or that entropy is decreasing across the entire galaxy. Instead, it describes a situation where specific parts of a galaxy exhibit characteristics we universally associate with youth, long after the system as a whole should have moved on to a more sedate, elderly phase. The most telling sign of a youthful galaxy is the presence of massive, hot blue stars. These stellar behemoths burn through their nuclear fuel in just a few million years, a mere blink of an eye on cosmic timescales. Their brilliant blue-white light dominates a galaxy's color, signaling an era of vigorous, recent starbirth. In a galaxy aging normally, these stars quickly vanish, leaving behind the longer-lived, cooler, redder stars that give older galaxies their characteristic ruddy glow. Therefore, when astronomers spot a galaxy that is predominantly red yet contains surprising, vivid pockets of blue light, they know they're looking at something unusual. It's the equivalent of finding a vibrant, youthful neighborhood in the middle of a city everyone thought was in decline. The galaxy isn't literally traveling back in time. It's experiencing a burst of rejuvenation that makes it look younger than it actually is. This rejuvenation is almost always triggered by an external event that delivers a fresh supply of cold gas, the raw material for making new stars. Imagine a campfire that has burned down to embers. If you were to suddenly throw a new stack of dry logs onto those embers, it would roar back to life with a new burst of flames. The fire isn't de-aging, it's being replenished. A galaxy operates on a similar principle. A galactic collision can violently funnel huge reservoirs of gas into its core, or it might slowly siphon fresh hydrogen from the invisible rivers of the cosmic web. This new fuel collapses under gravity to form new stars, lighting up the galaxy with the blue signature of youth. The galaxy's overall history remains. It still has its population of ancient red stars, but this new chapter of activity is written over the top of it, creating a complex and layered life story. Understanding this distinction is absolutely crucial. It moves us from a simplistic view of cosmic aging as a one-way street toward a much richer, more dynamic picture. Galaxies aren't just born, age, and die. They can experience revivals, second acts, and periods of renewed vigor. This concept doesn't break the rules of physics, it reveals their beautiful complexity. It shows us that a galaxy's apparent age is not a fixed date on a calendar but a snapshot of its current activity, heavily influenced by its environment and recent history. This flexibility is the key that unlocks a deeper mystery. If a galaxy's age can be so easily reset, what does that tell us about the nature of time itself on the grandest of scales? One of the most spectacular and violent events in the universe is also one of its greatest sources of renewal. When two galaxies are drawn together by their mutual gravitational pull, they don't simply pass by each other like ships in the night. Instead, they engage in a slow, majestic, and utterly chaotic dance that can last for hundreds of millions of years, a dance that ultimately ends in a colossal merger. During this process, the orderly structures of spiral arms are shredded and stretched into long, streaming tails of stars and gas. It is within this cosmic turmoil that the seeds of backwards aging are sown. The key to this rejuvenation lies in the gas. Galaxies are filled with immense clouds of hydrogen gas, the raw material for building new stars. In a quiet, isolated galaxy, this gas might be spread too thin or be too turbulent to collapse efficiently under its own gravity. But a galactic collision acts like a giant cosmic blender, violently mixing these gas clouds and driving them inward toward the galactic core. As these vast reservoirs of gas are compressed, their density soars, creating the perfect conditions for a monumental burst of new star formation. This event is known as a starburst, and it can flood a galaxy with millions of new, brilliant blue stars in a relatively short period of time. The effect is a dramatic reset of the galaxy's apparent age. A system that was once red and quiet, its star-forming days seemingly behind it, is suddenly ablaze with the blue light of youth. It's not that the old stars have vanished, they are still there. But they are now overwhelmingly outshone by this new, vibrant population of stellar youngsters. To an astronomer measuring the galaxy's color and spectrum, it suddenly looks far younger than it did before the collision. The clock, in a sense, has been turned back. A perfect example of this process is unfolding right now in a pair of galaxies known as the Antennae galaxies, located about 45 million light-years away. The name comes from the two long, curved tails of stars ejected by the collision that resemble an insect's antennae. Hubble Space Telescope images of this system are breathtaking. They show a chaotic whirlpool of dust, gas, and stars, punctuated by brilliant pink and red nebulae, the telltale signs of intense star-forming regions. Within these nebulae, thousands of star clusters are being born, some containing more stars than any cluster found in our own Milky Way. The Antennae galaxies are a stellar nursery operating at a frenetic pace, a place of destruction and creation happening simultaneously on an unimaginable scale. This presents a beautiful and profound irony. We often think of collisions in space as purely destructive events, and on the scale of individual solar systems, they certainly can be. But on the grand scale of an entire galaxy, the chaos of a merger is not an end. It is a catalyst. It is a violent, disruptive, and ultimately creative force that can breathe new life into aging structures, proving that in the cosmos, death and rebirth are often two sides of the same coin. While galactic collisions offer a dramatic and explosive path to rejuvenation, there exists another, more serene method for a galaxy to reclaim its youth, a gentle, continuous sip from the cosmic river. Picture the universe not as a collection of isolated islands, but as a vast, interconnected web. This is the cosmic web, a gigantic scaffolding of dark matter that stretches across the cosmos, and tracing along its filaments like dew on a spider's web are immense rivers of pristine, primordial gas. These are not the chaotic, turbulent flows of a merger, but steady, cold streams of hydrogen and helium that have remained largely unchanged since the dawn of time. When a galaxy, in its journey through space, happens to align itself with one of these cosmic filaments, it can tap into this endless reservoir of star-making material. This process is known as cold flow accretion. Unlike the violent compression of a collision, this is a more graceful and sustained infusion. The gas, chilled over billions of years, flows quietly along the dark matter highways and directly into the galaxy's waiting embrace. It's a silent, ongoing delivery of fuel, a constant top-up that can steadily replenish a galaxy's dwindling supplies. This incoming cold gas is particularly potent because it doesn't need to be shocked or compressed. It is already dense and ready to collapse under its own gravity, forming new stars with breathtaking efficiency. This mechanism was especially vital in the early universe, when the cosmic web was richer with these cold flows, allowing young galaxies to grow rapidly and sustain furious rates of star birth. But the truly fascinating part is that this isn't just ancient history. Astronomers have found evidence that even some modern, more isolated galaxies can still access these fossil rivers. In the quiet, sparsely populated voids between galaxy clusters where interactions are rare, a lone spiral galaxy might still be connected to this faint remnants of the cosmic web. By drawing in this fresh, unprocessed gas, it can maintain a low level of star formation, quietly resisting the reddening fade to old age that affects its cousins in busier environments. This reveals a crucial truth about galactic evolution. Galaxies are not doomed to a single, predetermined fate. They are dynamic systems, constantly interacting with their environment. Their life story is not just written internally but is profoundly shaped by their external connections. Whether through the violent shock of a collision or the gentle, persistent nourishment from the cosmic web, A galaxy's age is not a fixed date but a fluctuating state, a balance between the resources it consumes and the energy it expends. This ability to draw sustenance from the universe's hidden structures shows that rejuvenation is woven into the very fabric of cosmic design. But to truly grasp how these processes of rejuvenation are even possible, we must turn our attention to the most enigmatic player in the cosmic drama, dark matter. This mysterious substance, which far outweighs all the visible stars and gas in the universe combined, acts as the invisible skeleton upon which galaxies are built. We cannot see it, touch it, or directly observe it with any telescope because it does not emit, absorb, or reflect light. Its presence is known only through its immense gravitational influence, a ghostly pull that dictates the motion of stars and the fate of galaxies on the grandest scales. This gravitational influence is the key to understanding backwards aging. Picture a galaxy not as a simple island of stars, but as a luminous city nestled within a vast, invisible sphere of dark matter, a structure astronomers call a dark matter halo. This halo is not a passive container, it is an active gravitational engine. Its powerful pull is what first drew in the primordial gas that collapsed to form the galaxy billions of years ago, and it continues to govern the galaxy's growth and evolution to this day. The shape and size of this dark matter halo determine how a galaxy interacts with its environment, controlling the flow of cosmic resources. When fresh gas from the cosmic web flows toward a galaxy, it is the gravitational field of the dark matter halo that guides it inward, funneling it along specific pathways like water channeled into a river delta. In the case of a galactic collision, it is the interplay between the dark matter halos of the two galaxies that dictates the chaotic dance, stirring up the gas and driving it toward the center to ignite new stars. Furthermore, a massive, stable dark matter halo can act as a gravitational anchor, holding onto vast reservoirs of gas that might otherwise be blown away by stellar winds or supernova explosions. It effectively creates a protected storage tank of star-making fuel, a resource that can be tapped into later, perhaps during a quieter period, to trigger a new wave of star formation and give the galaxy a younger appearance. In this way, dark matter is the ultimate puppet master of galactic rejuvenation. It sets the stage, provides the resources, and directs the action, all while remaining hidden in the shadows. The phenomenon of backwards aging, which seems so miraculous and counterintuitive, is in many ways a direct manifestation of the subtle, unseen hand of dark matter, orchestrating the life cycles of galaxies across billions of years and reminding us that the true forces shaping our universe are often the ones we cannot see. This cyclical dance of death and rebirth is one of the most fascinating patterns in a galaxy's life. Unlike the singular, dramatic reset of a merger, quenching and rejuvenation represent a more rhythmic, internal heartbeat, a galaxy's own metabolic cycle. Quenching is the period of cosmic hibernation. It's the process where star formation is abruptly shut down. Imagine a thriving factory that suddenly has its power cut. The primary culprits behind this shutdown are often the very forces that once fueled the factory's success. When massive stars end their lives in supernova explosions, they don't just create heavy elements, they also unleash devastating shockwaves and torrents of high-energy particles that can heat the surrounding gas to millions of degrees or blow it completely out of the galaxy. This is like a factory's own machinery overheating and exploding, wrecking the facility and scattering its raw materials to the wind. An even more powerful quencher resides at the very center of many galaxies, a supermassive black hole. When this black hole actively feeds on surrounding gas and dust, it doesn't do so quietly. It becomes an active galactic nucleus, or AN, transforming into the most energetic engine in the universe. The infalling matter swirls into an accretion disk, heating up to incredible temperatures and blasting out intense radiation and colossal jets of plasma that travel at nearly the speed of light. These Aegean outbursts can flood the entire galaxy with so much energy that they prevent the cold gas from cooling and collapsing into new stars. They effectively sterilize the galactic environment, putting a definitive end to the star-forming era. For a time, the galaxy is quenched. Its blue stars fade away and it settles into its red and dead phase, appearing to have reached a permanent and quiet old age. But then the rejuvenation begins. This isn't a violation of physics. It's its next logical step. The same feedback processes that cause the quenching eventually settle down. The supernova explosions become less frequent as the population of massive stars dies out. The central black hole, having devoured all the readily available fuel, goes quiet, its furious jets shutting off. In the newfound silence, the hot, agitated gas that was blown around during the quenching phase begins to gradually cool. Over hundreds of millions of years, this gas radiates its heat away, condensing back into cold, dense clouds. Gravity takes over once more, pulling these clouds together until they reach the critical density needed to ignite a new generation of stars. From our distant vantage point, observing a galaxy over cosmic timescales that are mere snapshots to us, this creates the stunning illusion of backwards aging. A galaxy that we classified as elderly and retired suddenly from our perspective flashes with the blue light of newborn stars. It hasn't literally reversed time, it has simply completed a cycle. It's akin to a deciduous tree in winter, its branches bare and seemingly lifeless. To an observer who only sees it in that state, it appears old and finished. But with the return of spring, it bursts forth with new leaves and blossoms, displaying a vibrant vitality that seems to defy its previous state of decline. The tree hasn't reversed its age, it has entered a new phase of its cyclical life. This episodic nature of galactic evolution forces us to reconsider our metaphors for cosmic time. We often envision it as a linear arrow flying inexorably from a beginning to an end, but the quenching and rejuvenation cycles suggest that on galactic scales, time might be better understood as a series of pulses or seasons. There is a rhythm to the cosmos, a pattern of activity and rest, construction and destruction that repeats over vast eons. A galaxy's history is not a simple timeline but a layered tapestry, with epochs of youth written over epochs of age, each cycle leaving its distinct mark on the galactic structure. This reveals a universe that is not simply aging uniformly, but one where time unfolds in complex, recurring episodes, allowing for renewal and second acts billions of years in the making. So how do astronomers actually detect these cosmic Benjamin buttons? How can they possibly measure the age of a star millions of light years away, and then map that across an entire galaxy to find these pockets of unexpected youth? The answer lies in the light itself. Every star tells its own story through the light it emits, and astronomers have become expert translators of this cosmic language. The primary tool in their detective kit is a technique called spectroscopy. Think of it like this: when you see a rainbow, you're seeing sunlight split into its constituent colors. A spectrograph does this for starlight, but with infinitely more precision, spreading the light out into a detailed spectrum, a unique barcode that contains a wealth of information about the star that created it. Within that spectrum are specific dark lines like tiny fingerprints. These absorption lines are created by different elements in the star's atmosphere, each element absorbing light at a very specific wavelength. The pattern of these lines tells astronomers what the star is made of, but crucially, it also reveals its temperature, mass, and most importantly for our story, its age. Massive, hot, young blue stars have a very different spectral signature than older, cooler red stars. By analyzing the precise blend of these signatures coming from a specific region of a galaxy, scientists can essentially take a census of its stellar population. They can calculate the ratio of young, blue stars to old, red ones, giving them a reliable estimate of when the last major burst of star formation occurred in that area. It's like walking into a city and being able to tell if its population is mostly made up of teenagers, middle-aged adults, or senior citizens just by listening to the conversations happening on each street corner. But to do this for distant, faint galaxies, you need an incredibly powerful and sharp eye. This is where telescopes like Hubble and, more recently, the James Webb Space Telescope become absolute game changers. Hubble's keen vision allowed astronomers to resolve individual regions within relatively nearby galaxies, spotting those anomalous blue patches, and then using its built-in spectrographs to confirm their youthful nature. JWST, with its massive gold-coated mirror and ability to see in infrared light, has taken this to a whole new level. Infrared light pierces through obscuring clouds of cosmic dust that can hide star-forming regions from optical telescopes. This allows JWST to see the earliest stages of star birth, to catch galaxies in the very act of rejuvenation, and to perform this detailed spectroscopic analysis on galaxies so distant we are seeing them as they were just a few 100 million years after the Big Bang. It's the difference between seeing a blurry picture of a forest and being able to identify every single species of tree and the age of each one. The final step in this detective work is to create a map. Astronomers don't just take one spectrum of an entire galaxy. That would just give them an average age, masking the fascinating details. Instead, they use instruments that can take spectra at hundreds or even thousands of different points across a galaxy's face. They then compile this data to create a detailed age map, a colorful chart that visually highlights which neighborhoods are old and which are surprisingly young. It is on these maps that the evidence for backwards aging becomes undeniable. They might reveal a brilliant blue, youthful core shining within a vast, red expanse of ancient stars, or show young star-forming rings encircling an otherwise elderly galactic center. These maps transform an abstract theoretical idea into a tangible, visual reality. They are the conclusive proof that allows scientists to move beyond speculation and confidently say that yes, in certain places and under certain conditions, galaxies can indeed experience a dramatic and observable reversal of their aging process, giving us a direct window into the dynamic and ever-changing life story of the cosmos. Now, just as we start to think we understand these cycles of galactic death and rebirth, the universe presents us with an even more perplexing puzzle from its deepest past. Let's travel back in time to when the cosmos was only a few billion years old, a much more chaotic and crowded place. Here, astronomers using the Hubble and later the James Webb Space Telescope began to identify a peculiar class of objects. They were small, incredibly dense, and bluer than anything else in the sky. They were dubbed blue nuggets, and they have become one of the most fascinating case studies in the mystery of backwards aging. What makes these blue nuggets so strange is the sheer intensity of their star formation crammed into such a tiny volume. Imagine a galaxy no larger than a dwarf, but producing new stars at a rate hundreds of times faster than our own Milky Way. It's the cosmic equivalent of a tiny hummingbird with the metabolic rate of a blue whale. According to all our standard models, this kind of ferocious activity should be completely unsustainable. The powerful feedback from all those newborn stars, the stellar winds, and the inevitable supernova explosions should have blown away the remaining gas reservoir in a cosmic instant. effectively quenching the galaxy in a very short time and leaving behind a small, dead red nugget. And indeed, for many of these galaxies, that is exactly what happened. But the plot thickens. A significant number of these blue nuggets didn't follow the script. They didn't burn out. Against all odds, they managed to sustain their youthful, star-forming frenzy for much, much longer than anyone thought possible. They found a way to resist the self-destructive forces of their own incredible power, maintaining their brilliant blue cores for surprisingly long stretches of cosmic time. This is the very essence of backwards aging on a grand scale, a galaxy that by all rights should have aged into a red and dead state, but instead stubbornly clung to its youth. So how did they do it? How did these cosmic overachievers defy the inevitable? Astronomers believe the secret lies in their unique internal structure and their ability to protect their most valuable asset, cold gas. One leading theory suggests these galaxies possess an incredibly stable and massive central core, perhaps bolstered by a particularly dense and dominant dark matter halo. This powerful gravitational anchor acts like a cosmic vault, holding onto the gas supply with an immense grip. Even as supernova rage and try to blow the gas away, the galaxy's gravity is so strong that it can pull a significant portion of that ejected material back in a process known as recycling. It's a spectacular form of cosmic rain, where the very material expelled by dying stars eventually cools and falls back into the galaxy, ready to fuel the next generation of starbirth. Another possibility is that these blue nuggets are simply so efficient at accreting fresh gas from the cosmic web that they can constantly replenish what they lose. In the dense environments of the early universe, these rivers of primordial hydrogen were more plentiful, and a galaxy positioned at the right intersection of dark matter filaments could have a nearly endless supply of fuel delivered to its door. This constant top-up would allow it to maintain its star-forming fury, effectively freezing its evolutionary clock in a state of perpetual youth. Studying these ancient blue nuggets is like finding a perfectly preserved fossil that contradicts our textbook models of evolution. They are a powerful reminder that the universe always has more than one way to solve a problem. Their existence proves that galactic aging is not a one-size-fits-all process. It is a complex dance between a galaxy's internal fortitude and its external environment. Some galaxies succumb quickly to feedback, aging into quiet retirement. Others, like the blue nuggets, possess a rare combination of strength and fortune that allows them to rage against the dying of the light for eons, writing a far more dynamic and extended chapter in their life story, and showing us that even in the ancient universe, the cosmic clock could sometimes be made to tick much, much slower. Just as a person's life is profoundly shaped by their neighborhood and community, a galaxy's evolutionary path is deeply influenced by its cosmic address. Where a galaxy resides within the vast structure of the universe, whether in a bustling metropolitan center, a quiet suburban outskirts, or an isolated rural void, dictates the resources available to it and the challenges it must face, ultimately determining whether it ages gracefully, dies young, or experiences a surprising second youth. This environmental dependency adds a crucial layer of complexity to the mystery of backwards aging, revealing that a galaxy's fate is not written solely in its stars but also in its location. Consider first the extreme environment of a galaxy cluster, the megalopolis of the cosmos. These are dense cities of hundreds or even thousands of galaxies, all bound together by gravity and swimming in a superheated atmosphere of plasma known as the intracluster medium. For a galaxy living here, life is fast-paced and often brutal. As it moves through this dense, hot environment at incredible speeds, it experiences a phenomenon known as ram pressure stripping. Imagine a galaxy sailing through this intracluster medium like a car driving through a heavy downpour. The pressure of the impacting plasma acts like a powerful wind, violently stripping away the galaxy's cold gas reservoir, its precious star-forming fuel. This process is devastatingly efficient, leaving the galaxy gas-starved and unable to form new stars. The result is rapid and premature aging. A spiral galaxy that enters a cluster can have its gas ripped away, quenching its star formation and transforming it into a red, dead elliptical galaxy in a relatively short cosmic time. It's a classic case of a harsh environment accelerating the aging process. But even in these dense urban centers, there are opportunities for renewal, often found on the outskirts of the cluster. The regions between clusters are connected by the filaments of the cosmic web, and these filaments can still funnel cool gas toward the cluster's periphery. Galaxies that reside in these suburban zones of a cluster can sometimes avoid the full brunt of ram pressure stripping. More fascinatingly, they can find themselves in the path of this infalling gas. A galaxy orbiting the cluster's outer limits might periodically sweep through a dense river of this primordial hydrogen, accreting it and triggering a burst of star formation that makes it appear suddenly and anomalously young compared to its cluster-bound cousins. This is a perfect example of environmental rejuvenation, a galaxy's location providing it with a fresh source of fuel that locally reverses its aging trend. Now let's travel to the opposite extreme, the cosmic boondocks, isolated field galaxies, those that exist in the vast, empty voids between clusters and filaments, lead a very different existence. Here, life is quiet and slow. There are no violent collisions, no scorching plasma winds to strip away their gas. These galaxies are like solitary homesteaders with vast, untouched lands. They often retain large reservoirs of primordial gas, allowing them to form stars at a slow, steady, and sustained rate for billions of years. While they may not experience the dramatic, explosive bursts of rejuvenation that come from a galactic merger, their isolation allows them to preserve their youthfulness for extraordinarily long periods. They age at a glacial pace, their evolutionary clocks ticking far slower than those in the crowded clusters. In these quiet voids, a galaxy can remain blue and star-forming for most of the universe's history, effectively resisting the red and dead fate that befalls so many others. This stark contrast tells a powerful story. Backwards aging is not merely an internal affair, a simple question of a galaxy's mass or its central black hole. It is a drama played out between a galaxy and its environment. The same galaxy placed in a different location would live a completely different life. A gas-rich spiral destined for a long life of star formation in a void would be rapidly quenched and aged if it fell into a cluster. Conversely, an aging galaxy on the outskirts of a cluster might be given a new lease on life by a fortunate encounter with a filament of cold gas. This demonstrates that the cosmic neighborhood is a powerful actor in the story of time, capable of both imposing harsh deadlines and offering unexpected extensions. It forces us to see each galaxy not as an island, but as a citizen of a larger cosmic ecosystem, its history forever intertwined with the structure of the universe itself. Now, this cosmic flexibility in aging leads us to a deeper, more fundamental kind of time bending, one that isn't about galactic processes, but about the very fabric of space-time itself, as described by Einstein's revolutionary theory of relativity. This theory presents us with a universe where time is not a universal metronome ticking at the same rate for everyone. Instead, it's a fluid and personal experience, a dimension that stretches and compresses depending on two key factors, gravity and velocity. The stronger the gravitational field you're in, or the closer you are to a massive object like a planet or a star, the more time slows down for you relative to someone in a weaker field. Similarly, the faster you move through space, the slower your clock ticks compared to someone standing still. This isn't a theoretical abstraction, it's a measurable reality. The GPS satellites orbiting Earth have to constantly correct for these effects because their clocks run ever so slightly faster than clocks on the ground, and if they didn't, your navigation would be off by kilometers within a day. So, how does this mind-bending principle connect to our backwards aging galaxies? While relativity doesn't directly cause a galaxy to rejuvenate itself, it fundamentally underpins and complicates how we, as observers billions of light years away, perceive and measure its age. When we point our most powerful telescopes at a distant galaxy, we are not seeing it as it is now. We are catching a glimpse of how it was in the deep past, because the light from that galaxy has been traveling across the vast emptiness of space for millions or even billions of years to finally reach our lenses. We are literally looking back in time. This creates a cosmic version of time dilation. The farther away a galaxy is, the further back in its history we are observing. A galaxy 10 billion light-years away is being seen as it was 10 billion years ago, when the universe was young and chaotic. This presents a monumental challenge for astronomers trying to decipher a galaxy's true life story. Imagine you're a detective trying to determine a person's age, but you're only allowed to look at their childhood photographs. You might see a picture of a vibrant 10-year-old, but you have no way of knowing if that person is now a 30-year-old athlete or has already passed away of old age. Astronomers face a similar conundrum. When they detect a distant galaxy that appears blue and bursting with young stars, they must ask a critical question. Are we seeing a genuinely young galaxy, frozen in time from the universe's youth? Or are we looking at a galaxy that was already ancient by the time this light left it, but which has just experienced a recent massive rejuvenation event, a merger or a gas accretion, that makes it look young in this single, ancient snapshot? The light from that new burst of stars would be the first to arrive, telling a story of youth that may actually be a later chapter in a much longer book. This time dilation effect forces an incredibly careful and context-dependent interpretation of all our observations. It reminds us that a single measurement is just one frame in a long cosmic movie. To truly understand a galaxy's evolutionary path, to see if it's aging normally, slowing down, or even moving backwards, astronomers must piece together observations from galaxies at many different distances, effectively constructing a flipbook of galactic evolution. They have to compare that distant, seemingly youthful galaxy to closer, older galaxies that represent what it might eventually become, all while accounting for the relativistic effects that warp our view of time. This doesn't invalidate the discovery of backwards aging, it makes it all the more profound. It shows that the universe's flexibility with time operates on multiple levels. Not only can physical processes like mergers reset a galaxy's clock, but the very act of observing the cosmos forces us to acknowledge that time itself is not an absolute ruler but a flexible dimension, whose flow can be perceived in entirely different ways depending on where you are and how you're looking. This cosmic ability to reverse aging trends does far more than just add a new chapter to astronomy textbooks. It strikes at the very heart of a philosophical concept that has puzzled humans for millennia: the arrow of time. We experience time in our daily lives as an irreversible flow, a one-way street from the past through the present and into the future. You can remember yesterday, but you can't visit it. A shattered glass doesn't spontaneously reassemble itself on the floor. This intuitive sense of time's direction is so deeply ingrained in our perception of reality that we often consider it a fundamental law of the universe. But the discovery that galaxies can, in a very real sense, grow younger challenges this bedrock assumption. It suggests that on the grandest scales, time's arrow might not be as absolute or as uniform as we think. What we are seeing in these rejuvenating galaxies is not a violation of physics, but a magnificent demonstration of its nuance. It reveals that the arrow of time, while pointing firmly forward for the universe as a whole, can appear to waver, loop, or even reverse direction within local systems under the right conditions. A galaxy is not a closed box. It is an open system, constantly exchanging energy and matter with its vast surroundings. When two galaxies collide and funnel fresh gas into their cores, or when a lone spiral taps into a hidden river of primordial hydrogen, they are essentially importing order from outside. This influx of new, low-entropy material provides the means to locally reset the clock, creating pockets of youth and structure amidst the broader cosmic trend towards disorder. It is a powerful reminder that the flow of time is not a solitary current but a complex tapestry of countless threads, each moving at its own pace and sometimes even weaving backwards against the overall pattern. This idea resonates with some of the most profound questions in philosophy. For centuries, thinkers have debated whether time is a fundamental property of the universe or an emergent phenomenon that arises from more basic interactions. The phenomenon of backwards aging lends weight to the latter view. It suggests that what we perceive as the relentless forward march of time may actually be a statistical tendency, an overall drift towards higher entropy, rather than an inviolable law written into the foundation of reality. In most everyday situations, this statistical trend is so overwhelming that reversal is virtually impossible. But in the specific, high-energy, open environments of galaxies, the probabilities shift. The conditions allow for local decreases in entropy for processes that look, for all intents and purposes, like time running in reverse on a galactic scale. This doesn't mean that cause and effect break down or that we could ever witness stars unexploding or planets unforming. The fundamental laws of physics remain perfectly intact and time reversible at the microscopic level. But the emergent property we call the arrow of time, the thing we actually experience, shows itself to be flexible and context-dependent. It is a property that belongs to the system as a whole, not to its individual parts. This forces a profound shift in perspective. We can no longer think of time as a universal river flowing in one direction. Instead, we must see it as a landscape with hills and valleys. The overall slope of the landscape points downhill towards higher entropy, but within that landscape, there can be local hills where order temporarily increases and systems grow more complex and youthful. A backwards aging galaxy is standing on one of those hills, its apparent reversal made possible by the immense gravitational forces and energy flows at its disposal. This philosophical revelation transforms time from a tyrannical master into a dynamic and complex expression of the universe's structure, a property that emerges from interaction and that can, under extraordinary circumstances, tell a story that is far richer and more surprising than a simple, linear march into darkness. At first glance, the very idea of a galaxy growing younger seems to tear a hole in one of the most sacred principles of physics, the second law of thermodynamics. This law states that entropy, a measure of disorder or randomness, must always increase in any isolated system over time. It's the reason why a hot cup of coffee cools down to room temperature, never spontaneously reheating itself. It's why a tidy room inevitably becomes messy, and why we remember the past but not the future. The universe as a whole is on a one-way trip from a state of exquisite order to one of ultimate chaos and heat death. So how can a galaxy, a massive collection of stars and gas, possibly reverse this cosmic tide and become more ordered, more structured, and more youthful? The answer lies in a critical, often overlooked distinction: the difference between a closed system and an open one. The second law of thermodynamics is often misunderstood as a decree that disorder must increase everywhere at all times. But its power is absolute only within a perfectly closed system, one that has no interaction with the outside, no energy or matter coming in or going out. A galaxy is the exact opposite of a closed system. It is profoundly, magnificently open. It exists in a constant state of exchange with the vast universe around it. Think of it like a single city on Earth. A city can become cleaner, more organized, and more technologically advanced by importing resources, energy, and knowledge from other places. It can locally decrease its entropy, becoming a pocket of high order, even as the entire planet's overall entropy continues to increase. The city isn't breaking any laws, it's simply leveraging its connections to the wider world. A backwards aging galaxy operates on the same principle, just on a cosmic scale. When two galaxies collide, they aren't creating new energy or matter out of nothing. They are taking existing, diffuse clouds of primordial hydrogen gas, a state of relatively high entropy, and through the immense gravitational forces of the collision, compressing and organizing that gas into brilliant, new hot stars. This is a spectacular local decrease in entropy. The chaotic, random motion of gas particles is transformed into the highly ordered, structured, and energetic system of a star, with nuclear fusion blazing at its core. The galaxy appears younger because it has, quite literally, imported order from its environment and used it to build something new and magnificent. This process is entirely permitted by the laws of physics because the overall balance sheet of entropy still adds up. The tremendous release of energy from the supernova explosions of the short-lived massive stars, the intense radiation that heats the surrounding gas, and the chaotic turbulence stirred up by the merger itself, all of this waste heat and disorder is ejected back out into the intergalactic medium. The galaxy exports a huge amount of entropy back into its surroundings. So, while the galaxy's central region might be getting more ordered and youthful, the total entropy of the universe, when you account for everything that was expelled, has still increased. It's a magnificent cosmic bargain, a local, temporary reversal of aging paid for by an even greater export of disorder into the void. This thermodynamic perspective transforms the phenomenon from a mysterious paradox into a beautiful and natural consequence of how the universe operates. It shows us that the cosmos is not a simple, monotonous slide into darkness. It is a dynamic and ever-changing tapestry where the relentless increase of overall entropy provides the very background against which pockets of exquisite order can temporarily flourish. The second law doesn't forbid islands of youth. It demands that for every island there must be a corresponding ocean of disorder. The backwards aging galaxy is not a rebel breaking the laws of physics. It is a masterful economist working within the universe's fundamental rules to write a more complex and hopeful story. A story where even as the whole cosmos ages, the potential for local renewal, rebirth, and stunning beauty is written into the very fabric of physical law. Of course, we can see these incredible processes at work in the real universe, but how can we be sure we truly understand the underlying physics? How do we test our theories about galactic collisions and gas flows without waiting billions of years to see what happens? This is where the power of modern supercomputers comes into play, allowing us to create entire virtual universes where we can watch galaxies evolve from the Big Bang to the present day, all in a fraction of the time. Projects like the Illustris TNG simulation are at the forefront of this digital cosmology, and their results are nothing short of breathtaking. These aren't simple video game graphics. They are incredibly complex mathematical models that incorporate our best understanding of gravity, hydrodynamics, dark matter, and the life cycles of stars. Scientists feed the known laws of physics and the initial conditions of the early universe into these simulations, set them running, and then stand back to see what emerges. What they have found is absolutely crucial to our story. In these virtual cosmos, the phenomenon of backwards aging doesn't just happen as a rare glitch or a programming error. It emerges naturally and predictably as a direct consequence of the same dynamical processes we see in the real universe. The simulations show, in exquisite detail, how a massive elliptical galaxy that has been red and dead for eons can suddenly be rejuvenated. The digital telescope within the simulation might focus on a galaxy, and the algorithms will show a faint stream of cold gas, siphoned from a nearby cosmic filament, beginning to spiral into the galaxy's core. The code calculates the gravitational collapse, the compression, and the ignition of new stars. Right there on the screen, a region that was once a dull red begins to flicker, then glow with the brilliant blue light of millions of new stars. The galaxy's evolutionary clock, according to the metrics the scientists are tracking, has just been turned back. These virtual experiments are invaluable because they allow astronomers to run controlled tests that are simply impossible in the real world. In reality, we get a single, static snapshot of a galaxy's life. We see it at one moment in its multi-billion-year history and have to piece together its past and future from that single frame. But in a simulation, we have the ultimate time machine. We can rewind, fast forward, and pause. We can see the exact chain of events that led to the rejuvenation. Was it a minor merger with a small dwarf galaxy that provided just enough gas to trigger a small burst of star formation? Or was it a major, head-on collision that completely reshaped the galaxy's destiny? The simulation can show us with perfect clarity. We can even run the same simulation over and over again, changing one tiny variable each time, like the angle of a collision or the amount of gas available, to see how it alters the outcome. This process allows scientists to isolate the key mechanisms behind backwards aging and confirm that our physical theories are robust enough to predict this astonishing behavior. In this way, these monumental computational efforts act as the essential bridge between raw theory and hard observation. A theorist can propose an elegant mathematical reason for why a galaxy might rejuvenate, but until that idea is tested in a realistic simulation that produces a galaxy matching the ones we see with Hubble and Webb, it remains just an interesting idea. Conversely, when an observer spots a bizarre, backwards aging galaxy in the night sky, they can turn to the simulators and ask, "Can your models produce something that looks like this?" And if the answer is yes, it provides a powerful vote of confidence that we are on the right track. These digital universes have become the ultimate cosmic sandbox, a playground for testing our most profound ideas about time, aging, and evolution on the grandest of scales. They show us that the universe's capacity for renewal isn't a flaw in our understanding, but a beautiful and emergent feature of its underlying design. Yet for all their destructive power, these cosmic engines hold a paradoxical creative potential. In certain precise conditions, the very same jets that can sterilize a galaxy of its star-forming fuel can also act as cosmic sculptors and triggers. When a supermassive black hole's outburst is not too powerful, a gentle sigh rather than a full-blown scream, its effects can be surprisingly constructive. Imagine those colossal jets plowing into the massive molecular clouds that drift through the galactic halo. Instead of simply vaporizing the cloud, the leading edge of the jet can act like a tremendous plow, sweeping up the gas and compressing it into incredibly dense shells and layers. This process, known as jet-induced star formation, takes a cloud that was too diffuse to collapse on its own and squeezes it past the critical threshold. The result is not destruction but the forced birth of new stars. It's a spectacular irony, the galaxy's most potent force of destruction becoming the midwife for a new generation of stellar life. This creates a fascinating feedback loop, a kind of cosmic thermostat regulating the galaxy's life cycle. A period of intense black hole activity quenches star formation, eventually starving the black hole itself of fuel and causing its outburst to subside. In the ensuing quiet, gas can gradually cool and accumulate once more. Then, when a new trickle of gas reaches the black hole, it might trigger a smaller, more focused jet that then compresses nearby gas clouds and sparks a localized burst of new star formation. From our distant vantage point, observing this cycle over epochs, the galaxy would appear to flicker with youth intermittently. It would spend long periods as a red, quiescent system, only to suddenly and paradoxically sprout brilliant blue regions of young stars, seemingly turning back its own clock before settling down again. This episodic rejuvenation, driven by the black hole's complex influence, paints a picture of galactic aging that is not a smooth decline, but a series of stops and starts, of long sleeps punctuated by brief, brilliant awakenings. This dual role utterly transforms our view of supermassive black holes. They are not simple monsters lurking in the dark, mere consumers of matter and light. They are dynamic regulators, fundamental forces that shape the destiny of their entire host galaxy. Their immense gravity provides the anchor around which the galaxy formed, and their incredible energy output governs its ongoing evolution. They can be agents of death, imposing a premature old age by shutting down star birth, but they can also, under the right circumstances, be agents of creation and renewal, triggering the very processes that lead to a galactic renaissance. This complex and counterintuitive behavior is a powerful reminder that in the cosmos, the same force can often wield both a sword and a pen, capable of ending stories and writing surprising new chapters in the endless, dynamic biography of a galaxy. This stark contrast between the life cycle of a star system and that of a living creature reveals a profound truth about the language we use to describe the cosmos. When we say a galaxy is aging, we are employing a powerful metaphor, a conceptual bridge that helps our minds grasp processes spanning billions of years. But we must be careful not to let the metaphor obscure the reality. Biological aging, as we experience it, is often a story of inevitable, one-way decline. It is governed by internal clocks, like the shortening of telomeres with each cell division, a pre-programmed march toward a finite endpoint. An organism's vitality wanes, its systems gradually fail, and this trajectory is largely locked in by its genetic blueprint. A galaxy, however, operates under an entirely different set of rules. Its age is not a countdown to a predetermined death, but a shifting balance between competing forces. It is a statistical story told not by the fate of a single star, but by the collective behavior of billions of them, and it is an environmental story dictated by external events like collisions and gas accretion that can arrive at any moment, completely resetting the narrative. A galaxy doesn't have a fixed expiration date. It has a history, a series of chapters written by its interactions with the wider universe. A red and dead galaxy isn't deceased, it's dormant, and as we've seen, it can be violently and spectacularly awoken from that slumber. This cosmic aging is a story of evolution and change, not an inevitable senescence. This comparison enriches our understanding of time itself. It shows us that aging is not a single, universal process, but a concept that takes its meaning from the structure and context of the system in question. Time's impact is relative. For a mayfly that lives only a day, an hour is a significant portion of its life. For a galaxy, 100 million years is merely a brief episode. For a human, aging is a linear personal journey. For a galaxy, it is a cyclical dance with its environment. Recognizing this relativity allows us to appreciate the unique rhythms of the cosmos. It frees us from projecting our own biological imperatives onto the universe and lets us see it on its own terms. A vast, dynamic arena where time weaves narratives of change, renewal, and transformation on scales so grand they humble our earthly conceptions of life and death. This cosmic capacity for renewal inevitably leads us to a breathtaking question about the grandest scale of all. If individual galaxies can find ways to reverse their aging, could the entire universe somehow cheat its own predicted fate? For over a century, the most widely accepted forecast for our cosmos has been a rather bleak and lonely one: the heat death. This is the idea that as the universe continues to expand and accelerate, all stars will eventually burn out, all matter will disperse, and everything will cool to a uniform, frigid temperature just a fraction of a degree above absolute zero. In this ultimate state, no energy gradients will remain, no work can be done, and all cosmic activity will cease forever in a state of maximum entropy. It is the final, silent equilibrium of everything. The discovery that galaxies can experience local rejuvenation does not overturn this profound and sobering prediction. The laws of thermodynamics still hold supreme on the universal scale. The overall entropy of the cosmos continues to increase, and the expansion driven by dark energy appears relentless and unstoppable. The energy imported by a galaxy to fuel its rebirth is not created from nothing. It is borrowed from its immediate surroundings, and the net result is still an overall increase in disorder when you account for the entire system. A galaxy's fountain of youth is not a challenge to the universe's ultimate fate, but rather a spectacular, localized exception that proves the rule. However, what this phenomenon does suggest is that the long, slow journey toward that final state could be far more interesting, complex, and vibrant than we ever imagined. The path to heat death may not be a smooth, monotonous slide into darkness. Instead, it could be a gradual fading punctuated by brilliant, long-lasting flashes of activity. Think of it not as a single, final sunset, but as a twilight that lasts for trillions of years, filled with occasional, stunning bursts of light and color. As the universe expands and most galaxies age into darkness, the processes of mergers and cold gas accretion could continue in isolated pockets, especially within the largest, most massive galaxy clusters that act as gravitational anchors. These cosmic metropolises could become the last bastions of activity, the final flickering candles in an increasingly vast and dark room. Within these enduring structures, the cycle of stellar death and rebirth could continue for an almost unimaginable length of time. While the majority of the universe has grown cold and dark, these privileged pockets might still host galaxies that are actively colliding, merging, and drawing in the last remnants of primordial gas, sparking new generations of stars. This means that the era of cosmic habitability, the window of time in which conditions are right for planets and, potentially, life, could be extended by tens of billions of years beyond what we previously thought, not universally, but in these specific, fortunate islands of matter. The universe's story, therefore, may not be a simple tragedy ending in silence. It could be a far more nuanced epic, a narrative where the overarching theme is indeed decline, but one that contains incredibly long and rich chapters of persistence, struggle, and localized beauty, reminding us that even within the most certain of fates, there is room for surprise and wonder on a scale that dwarfs all of human history. Pinpointing these cosmic acts of rejuvenation is one of the most delicate and difficult tasks in modern astronomy. The central challenge lies in the starlight itself. When we look at a galaxy, we are not seeing a simple, single-age population. We are looking at a complex blend of light from stars of all different ages, all shining at once. Distinguishing the faint, blue glow of a few million newly formed stars from the dominant redder light of billions of ancient stars is like trying to hear a single flute playing a new melody in a symphony orchestra that has been performing the same piece for eons. The new notes are there, but they are almost drowned out by the established harmony. This problem is compounded by a host of observational biases. One of the most significant is what astronomers call the progenitor bias. Imagine we observe two galaxies that look identical in every way. Same mass, same shape, same overall color. One, however, is genuinely young, having formed all of its stars in a single, recent burst. The other is a much older galaxy that has just experienced a major merger and is now in the throes of a powerful, backwards aging rejuvenation. From our distant vantage point, using the tools we have today, these two galaxies can appear virtually identical in a single snapshot. We might easily mistake the recently rejuvenated galaxy for a genuinely young one, completely misreading its complex life story. Without the ability to watch it over billions of years, we are forced to rely on incredibly subtle clues hidden in its light to tell the difference. Furthermore, our view is often obscured by cosmic dust, vast clouds of fine particles created in the atmospheres of old stars and in supernova explosions can drift through a galaxy. This dust is extraordinarily effective at absorbing blue light and re-radiating it as heat, which we see as infrared radiation. A galaxy that is undergoing a massive burst of star formation could have its brilliant blue light completely hidden behind these dusty veils, making it appear much redder and older than it truly is. It's like trying to judge the health of a forest by looking at it through a thick, smoky fog. You might completely miss the vibrant new saplings sprouting up beneath the canopy. This is precisely where the next generation of astronomical observatories promises to revolutionize our understanding. The Nancy Grace Roman Space Telescope, set to launch later this decade, will act as an unparalleled cosmic surveyor. Its wide-field infrared camera will be able to map large swaths of the sky with Hubble-like clarity, but a field of view over 100 times larger. This will allow astronomers to find and catalogue thousands of these rare backwards aging galaxies, moving from studying a handful of curious examples to analyzing a vast population. We will be able to see how common rejuvenation really is and under what specific conditions it occurs, turning anecdotal evidence into solid statistical science. On the ground, the Extremely Large Telescope, or ELT, will take detail to a whole new level. With a primary mirror nearly 40 meters across a colossal eye on the sky, it will gather enough light to perform incredibly detailed spectroscopy on individual stars within galaxies millions of light-years away. The ELT won't just see that a galaxy has a blue patch. It will be able to measure the precise ages and chemical compositions of the stars within that patch, effectively allowing us to read the exact date on that galactic clock reset. It will peer through the obscuring dust with its powerful infrared instruments, revealing the hidden stellar nurseries that current telescopes can only infer. Together, these missions will act as a time machine with a focus dial we've never had before. They will allow us to not just see that a galaxy appears younger, but to understand the precise trigger. Was it a specific type of merger? The accretion of gas from a particular filament of the cosmic web. the delayed feedback from a supermassive black hole. By refining our models with this exquisite new data, we move from simply documenting the phenomenon of backwards aging to truly comprehending its mechanics. Each new observation will be a crucial piece of the puzzle, helping us assemble a complete picture of galactic life cycles, and in doing so, deepening our grasp of time itself as a flexible and dynamic dimension of our universe. Long before telescopes or supercomputers, humanity grappled with the nature of time, weaving its mysteries into the very fabric of our stories and beliefs. Ancient cultures from the Greeks and Hindus to the Mayans often saw time not as a straight line, but as a great wheel, turning through endless cycles of creation, preservation, and destruction. In these cosmologies, the universe itself was subject to periods of flourishing and decay, of golden ages darkening into iron ones, only to be purified by fire or flood and born anew. This was a time of eternal return, where the end of one story was always the beginning of the next, a concept vividly captured in the Hindu notion of cosmic cycles, or yugas, that repeat across unimaginable eons. In stark contrast, the Abrahamic traditions of Judaism, Christianity, and Islam introduced a powerfully linear conception of time. Here, history has a definitive beginning, a central narrative of prophecy and revelation, and an ultimate, final ending, a day of judgment, a messianic age, a point of culmination after which nothing will be the same. This view presents time as an arrow, launched from a singular creation event and flying irreversibly toward a predetermined destiny. For centuries, this linear perspective heavily influenced Western science, framing our early models of cosmic evolution as a one-way journey from a big bang to a final, silent heat death. The breathtaking discovery that galaxies can, in a very real sense, experience renewal and reverse their aging presents a fascinating twist in this age-old dialogue. It doesn't validate one ancient myth over another, but it does create a profound and unexpected resonance with those cyclical worldviews. Modern astrophysics, with its cold equations and precise instruments, has revealed a universe where decay and renewal are not just philosophical concepts but active, observable processes. A galaxy that was red and dead, the very picture of cosmic old age in our linear models, can be violently and spectacularly reborn through a collision or gently rejuvenated by a slow sip of cosmic gas. The universe, it seems, operates on a principle of cyclical regeneration on the grandest scales. This creates a beautiful synergy between the oldest stories we've told ourselves and the newest data from our most advanced observatories. It demonstrates that scientific discovery does not simply erase ancient wisdom. Sometimes it rediscovers its essence in a new language. We now have empirical evidence that the cosmos itself participates in a form of the cycles our ancestors imagined, not because of capricious gods, but because of the immutable laws of physics governing gravity, dark matter, and hydrodynamics. This connection transforms our cultural narrative about time from a matter of pure belief into a conversation enriched by evidence, showing that our place in the cosmos is part of a much older and more continuous human quest for understanding. Ultimately, this resonance between the ancient and the modern does more than just validate old ideas. It transforms them. It invites us to see our own stories of death and rebirth, of decline and renaissance, not as mere metaphors but as reflections of a deep, structural pattern woven into the universe itself. The discovery that galaxies age backwards tells us that renewal is not just a hopeful human idea, but a fundamental capability of the cosmos. It suggests that the universe has a built-in capacity for second acts, for complexity to re-emerge from simplicity, and for new beginnings to be written over old endings, offering a perspective that is both scientifically rigorous and deeply, poetically meaningful. This line of questioning leads us directly to one of the most profound and debated ideas in all of science and philosophy, the anthropic principle. In its simplest form, the anthropic principle suggests that any observations we make about the universe must, by necessity, be compatible with the existence of conscious, observing life. We are here to see it, so the universe must have properties that allowed for our emergence. It's a statement that seems almost too obvious, but its implications are staggering when applied to the fundamental constants of nature. Why is the force of gravity exactly as strong as it is? Why is the cosmological constant so finely tuned? If any of these values were altered by even a tiny fraction, atoms would never form, stars would never ignite, and life as we know it would be impossible. The universe seems suspiciously well suited for our existence. Now, let's bring this back to our backwards aging galaxies. If galactic rejuvenation can extend a galaxy's period of vitality, could it also extend its window of habitability? A galaxy that is repeatedly rejuvenated avoids becoming a red and dead relic. It continues to produce new generations of stars, and with those stars come new planetary systems. This ongoing cycle of stellar birth doesn't just provide more opportunities for planets to form, it also enriches the galactic environment with heavier elements over many generations. Elements like carbon, oxygen, and iron, which are forged in stellar cores and scattered by supernova, are the essential building blocks of planets and life itself. A galaxy that experiences multiple episodes of star formation is essentially recycling its materials, creating a richer and more complex cosmic ecosystem over time. This presents a fascinating, though highly speculative, possibility. Could it be that the processes of galactic rejuvenation, mergers, gas accretion, and the cyclical feedback from black holes are not just cosmic curiosities? Could they actually be a necessary prerequisite for the development of advanced life? A universe where all galaxies strictly followed the standard model and aged into quiet retirement might be a far less interesting place. In such a universe, the window for star formation, and thus for planet formation and the evolution of life, might be much shorter. The chances for a stable, long-lived solar system like ours to emerge might be drastically reduced if the entire galactic neighborhood had already shut down its production lines billions of years earlier. By this line of thinking, the phenomenon of backwards aging might be more than just an interesting exception to a rule. It could be a crucial feature of a universe that is capable of sustaining complexity and consciousness over cosmological timescales. It provides a mechanism for the cosmos to keep the lights on for longer in certain regions, increasing the odds that somewhere, somehow, a species might arise to look back and wonder about it all. This doesn't mean the universe was designed for life, but it does suggest that the same physical laws that govern the collisions of galaxies also, inadvertently, create conditions that are far more amenable to our existence. We are not just passive observers of these grand cosmic cycles. We are perhaps their ultimate beneficiaries, living proof that in a universe capable of resetting its own clocks, the story of life has more time to write itself. Perhaps the most radical implication of these galactic rejuvenations is that they nudge us toward a revolutionary idea in fundamental physics, that time itself may not be a primary ingredient of the universe, but something that emerges from more basic, underlying processes. We are so accustomed to experiencing time as a fundamental, flowing reality that the suggestion it might be an illusion, a byproduct, feels almost unthinkable. Yet, this is precisely what the concept of time as an emergent property proposes. Think of it like temperature. When you touch a hot stove, you feel heat, a single, tangible sensation. But that sensation isn't a fundamental force. It emerges from the frantic, chaotic jiggling of trillions of individual atoms and molecules. The property we call temperature doesn't exist for a single atom. It only has meaning for a vast collection of them. In a very similar way, some physicists theorize that what we perceive as the flow of time might not be a fundamental feature of reality, but a collective phenomenon that arises from the complex interactions of countless more basic quantum elements. This is where the phenomenon of backwards aging galaxies becomes more than just a curious astronomical anomaly. It becomes a piece of potential evidence in one of physics' greatest mysteries. These galaxies demonstrate that the arrow of time, its apparent one-way direction from order to disorder, is not an absolute, inviolable law written into the cosmos at its birth. Instead, it appears to be a trend that can be bent, paused, or even locally reversed by specific conditions and interactions. A galaxy's apparent age is not a fixed date but a fluctuating state, heavily dependent on whether it's isolated or colliding, gas-rich or gas-starved. It now is dictated by its environment and its history. This profound context dependence supports the emergent time hypothesis. It suggests that time's arrow is not a universal constant but a statistical tendency, a large-scale pattern that emerges from countless smaller events, much like the overall pressure in a gas emerges from the random motions of its particles. This perspective forces a complete shift in our metaphysical understanding of reality. If time is emergent, then the universe at its most fundamental level might be timeless. The quantum processes from which time emerges could be static and unchanging, existing in a state of pure potential sometimes called the quantum foam. From this eternal, chaotic foundation, the familiar dimensions of space and time crystallize as the universe cools and expands, much like ice crystals forming in a uniform layer of freezing water. Our conscious experience of a moment called now, flowing from a past we remember into a future we anticipate, would then be a kind of cognitive illusion, a story our brains construct to make sense of this emergent statistical flow. The backwards aging galaxy is a cosmic signpost pointing to this deeper truth. It shows us a place where the smooth, emergent narrative of time has developed a kink, a plot twist, revealing the more complex, timeless reality operating beneath the surface. It hints that our entire experience of existence is a beautiful and compelling derivative of something far stranger and more magnificent. Now, with all these mind-bending ideas about galactic rebirth and flexible time, it's absolutely vital that we pause and tackle some of the biggest misconceptions head-on. The phrase backwards aging is incredibly evocative, and it's easy for our imaginations to run wild with visions of time machines and stars literally rewinding their lives. But the reality, while no less spectacular, is firmly grounded in physics as we understand it. First and foremost, this phenomenon has nothing to do with the science fiction concept of time travel. We are not seeing galaxies violate causality where effects precede their causes. You won't find a star that explodes as a supernova and then reassembles itself from the expanding nebula. The fundamental, unbreakable rule that cause must always come before effect remains perfectly intact. What we are observing is not a reversal of time itself, but a reversal of a specific evolutionary trend. Think of it like a forest that has matured and is dominated by ancient, towering trees. If a massive wildfire were to sweep through, it would be devastating, but it would also clear the canopy and allow sunlight to reach the forest floor. This could trigger a massive regrowth of saplings, creating a dense, young understory beneath the surviving old-growth trees. From an ecological perspective, the forest has suddenly become much younger in its overall composition, even though the oldest trees are still there. The wildfire didn't reverse time, it reset the conditions for growth. A galaxy experiencing a burst of rejuvenation is doing the same thing on a cosmic scale. It's not traveling back in time. It's using a fresh injection of resources to start a new chapter of star formation that makes it look younger according to the standard metrics we use. Another crucial point is that this is not a universal rule. The overwhelming majority of galaxies in the universe are, in fact, aging exactly as our standard models predict. They form their stars, use up their gas, and gradually redden into quiet retirement. These backwards aging galaxies are the fascinating exceptions, not the new rule. But in science, it's often the exceptions that are the most valuable. They are the outliers that point to gaps in our understanding, the clues that force us to refine our models and dig deeper. The discovery that some galaxies can rejuvenate doesn't mean our previous theories of galactic evolution are wrong. It means they were incomplete. We now understand that a galaxy's life story isn't just a single, predetermined path. It's a branching narrative with possibilities for dramatic plot twists, depending on its environment and interactions. This process of nuance and refinement is the true engine of scientific progress. It's not about grand revolutions that completely overthrow old ideas overnight. More often, it's a gradual, meticulous process of adding new layers of complexity to our existing knowledge. The core principles of gravity, star formation, and thermodynamics still hold absolutely true. What has changed is our appreciation for how these principles can combine in dynamic and unexpected ways to create outcomes we hadn't previously imagined. This is how science truly works, not as a rigid set of facts, but as an ever-evolving and self-correcting conversation with the universe, one where the most exciting discoveries often come from listening carefully to the whispers of the exceptions. You might be wondering, with all this talk of galactic rebirth and cosmic time, what's in it for us down here on Earth? It's a fair question. After all, funding for massive telescopes and supercomputer simulations doesn't come from nowhere. It represents a profound investment in our collective curiosity. The most honest answer is that studying the rejuvenation of galaxies a billion light-years away will not directly lead to a faster smartphone processor or a more efficient electric car battery tomorrow. This is fundamental blue-sky research in its purest form. It seeks to answer questions for the sake of understanding itself, driven by a desire to comprehend the strange and beautiful universe we find ourselves in. But history has shown us time and again that the pursuit of fundamental knowledge has a funny way of circling back with astonishingly practical benefits. The equations James Clerk Maxwell formulated to unify electricity and magnetism in the 1800s didn't just explain light. They became the foundational bedrock for every single wireless technology we use today, from radio to Wi-Fi to your smartphone itself. The strange and counterintuitive world of quantum mechanics, explored by physicists trying to understand the atom, didn't just satisfy intellectual curiosity. It gave us the transistor, the laser, and the entire digital revolution. We simply cannot predict which thread of pure inquiry will eventually weave itself into the fabric of our daily lives. The physics we are unraveling by studying galactic collisions and dark matter halos is the most complex there is, dealing with gravity, particle interactions, and high-energy environments we can't possibly recreate in a lab on Earth. Who is to say that a deeper grasp of these principles won't, decades or centuries from now, reveal insights into energy, materials, or forces that we can't even conceive of today? Beyond these potential future spin-offs, this research is already driving tangible technological innovation right now. The challenge of observing these faint, distant objects pushes engineers to design ever more sensitive detectors and more powerful telescopes. The algorithms developed to process the immense data deluge from the James Webb Space Telescope, filtering out cosmic noise to reveal the faint whisper of a rejuvenating galaxy, have applications in medical imaging, climate science, and artificial intelligence. The mind-boggling computational power required to run universe-scale simulations forces computer scientists to break new ground in processing power and data handling, advances that inevitably trickle down to benefit other fields of science and industry. The quest to understand cosmic time is in itself a powerful engine for technological progress. Yet, to measure the value of this endeavor solely by its potential for practical application is to miss its most profound impact. This pursuit feeds something fundamental to the human spirit, our insatiable curiosity. For thousands of years, we have looked up at the night sky and wondered about our place in the grand scheme of things. Are we alone? How did it all begin? How will it all end? The discovery that galaxies can reverse their aging adds a breathtaking new layer to that story. It tells us that the universe is not just a clock winding down. It is a dynamic, creative, and surprisingly resilient system. It enriches our culture, our philosophy, and our art by providing a more nuanced and awe-inspiring narrative of cosmic history. It reminds us that we are part of a story far grander and more mysterious than our everyday concerns, a perspective that fosters humility, wonder, and a deeper appreciation for the incredible complexity of reality we are privileged to witness and explore. Witnessing the cosmos engage in these acts of renewal can't help but spark a profound reflection within us about our own fleeting existence. If time itself can be bent and reshaped on such a grand scale, if entire galaxies can find a second wind, what does that suggest about our own human journey? It's not that we can directly copy the violent mechanics of a galactic merger, but the metaphor is undeniably powerful. It invites us to consider the boundaries of our own vitality and the ethical landscape of extending it. For centuries, humanity has viewed aging as an immutable fate, a one-way path we all must walk. But the cosmic example challenges that fatalism, not by offering a simple solution, but by expanding our imagination of what might be possible. It fuels a hopeful, yet deeply cautious, curiosity about whether we might one day learn to gently influence our own biological clocks, to mitigate the ravages of time not with science fiction, but with a deeper understanding of the natural processes that govern life itself. This spark of hope, however, must be tempered with a heavy dose of wisdom and ethical consideration. The universe's method of rejuvenation is often violent and chaotic, a galactic collision that would spell utter doom for any planetary system caught in the crossfire. It is a blunt, indiscriminate force of nature. Our approach, by contrast, must be one of nuance and profound respect. The pursuit of life extension or enhanced vitality isn't just a technical challenge, it's a philosophical minefield. Who would have access to such technologies? Could extending the human lifespan exacerbate social inequalities, creating a new chasm between those who can afford more time and those who cannot? And perhaps most importantly, if we were to significantly prolong our years, what would give those years meaning? A galaxy doesn't ponder its purpose, it simply obeys the laws of physics. We, however, are defined by our narratives, our relationships, and our sense of a life well lived. Extending the quantity of our days without enriching their quality could lead to a hollow existence, a long life devoid of the very things that make it worth living. This cosmic perspective ultimately gifts us a more balanced and appreciative view of time's passage. A galaxy that rejuvenates doesn't erase its history, it layers new youth over ancient foundations. In the same way, our own lives gain their depth and richness from the entire spectrum of experience. The vigor and potential of youth are magnificent, but they are not the sole measures of a valuable life. The wisdom, perspective, and hard-earned resilience that come with age are equally precious treasures. The cosmic dance of stars teaches us to value every phase of the cycle, not to desperately cling to one at the expense of appreciating the others. It argues against a culture obsessed with youth alone and reminds us that a life well lived is a tapestry woven from threads of both bold action and quiet reflection, of both discovery and acceptance. Ultimately, the lesson from these distant galaxies is that time is not merely a currency to be spent, but a dimension to be understood and respected. Their story encourages us to shift our gaze from simply trying to add more years to our life and to focus instead on adding more life to our years. It calls for a responsible science that seeks to alleviate suffering and enhance human potential, but always with a guiding ethical compass that prioritizes dignity, equity, and the profound, inherent value of every individual's journey from beginning to end. The universe shows us that renewal is possible, but it is our human responsibility to ensure that our pursuit of it is guided not just by ambition, but by compassion, wisdom, and a deep reverence for the natural arc of a meaningful existence. This incredible interplay of cosmic death and rebirth doesn't just belong to the realm of astronomy. It acts as a powerful bridge, connecting seemingly distant fields of human thought in a shared conversation about time, existence, and beauty. The mystery of backwards aging galaxies is a perfect example of how the biggest questions in the universe cannot be contained within a single academic department. They spill over, inviting physicists, philosophers, and artists to the same table, each bringing their own unique tools to help us see the problem in a new light. Consider the role of the artist. How do you possibly visualize a galaxy growing younger? This is not a challenge of simply reproducing a Hubble photograph. It is an act of profound imagination and interpretation. Digital artists and data visualizers take the complex information from telescope spectra and supercomputer simulations, the cold numbers representing star formation rates and gas density, and translate them into stunning visual narratives that our minds can intuitively grasp. They create animations that show the graceful, silent dance of two galaxies merging, their structures warping and flowing as rivers of blue light ignite within their cores. They paint visions of the cosmic web, portraying those invisible filaments of dark matter as luminous highways upon which rivers of primordial gas flow into waiting galaxies. This work is far more than just illustration. It is a crucial form of translation. It takes the abstract, mathematical language of astrophysics and renders it into a visual poetry that engages the public's wonder and curiosity in a way that a graph or an equation never could. It makes the unimaginable tangible, fostering a deeper emotional connection to the cosmos and reminding us that science and art are not opposites, but two different languages telling the same magnificent story. Meanwhile, philosophers engage with this discovery on an entirely different plane, probing the metaphysical implications. For centuries, they have debated the nature of time. Is it a fundamental reality or a mere illusion of human consciousness? Does it flow in one direction, and if so, why? The concrete observation that a galaxy's apparent age can be reset by a collision provides a new, real-world anchor point for these ancient debates. It gives philosophers a physical phenomenon to grapple with, moving the discussion from pure abstraction into a dialogue with empirical evidence. A philosopher of science might ask what these galactic reversals mean for our very definition of aging. If a process can be reversed, can we truly call it aging in the same way we do for biological organisms? This kind of crosstalk is immensely fruitful. It forces scientists to carefully refine their own definitions and assumptions, while it gives philosophers a fresh and exciting playground of ideas rooted in the latest discoveries of how the universe actually behaves. The collaboration pushes both fields to greater clarity and depth, proving that the telescope and the thinking chair are complementary instruments for exploring reality. This interdisciplinary dialogue reveals a fundamental truth about the pursuit of knowledge. The most profound mysteries are never solved in isolation. The puzzle of cosmic time requires the physicist's equations, the astronomer's observations, the computational power of the computer scientist, the interpretive skill of the artist, and the critical scrutiny of the philosopher. Each perspective illuminates a different facet of the gem. A scientist might calculate the exact amount of gas needed to trigger a starburst, while an artist helps us feel the awe of that event, and a philosopher helps us comprehend what it means for our understanding of existence itself. This collaborative spirit is our greatest asset as we reach further into the cosmos, reminding us that the universe does not respect the boundaries we draw between our academic disciplines. The most compelling answers will always be found in the fertile spaces where different ways of knowing meet, converse, and together build a richer, more complete picture of our wondrous and perplexing home. Have you ever found yourself staring up at a star-dusted night sky, your mind drifting beyond the familiar constellations, and truly wondering if the flow of time itself might be different out there? It's a dizzying, almost vertigo-inducing thought. We're so anchored to our earthly experience of time as a relentless, one-way river that the idea of a place where that river could slow, swirl, or even momentarily flow backwards feels like pure fantasy. But as we've journeyed through the story of these rejuvenating galaxies, that fantasy inches closer to a breathtaking scientific possibility. So I want to extend that sense of wonder directly to you. Let's play with that idea together for a moment. Close your eyes and picture it. You're the captain of a spacecraft with the ultimate viewing deck, and you've just arrived in the vicinity of a galaxy that is actively experiencing a massive rejuvenation event. What does your cosmic windshield actually show you? It wouldn't be like watching a movie in rewind with stars collapsing back into gas clouds. Instead, you'd be witnessing a spectacle of creation so intense it would dwarf anything in our quiet galactic neighborhood. Imagine the core of the galaxy, not as a serene, yellowish hub of old stars, but as a maelstrom of incandescent blue and violet. Brilliant, short-lived supergiant stars, dozens of times more massive than our Sun, are igniting in waves, flooding space with ultraviolet light that causes vast clouds of surrounding gas to glow in ethereal pinks and reds like a cosmic neon sign. You might witness the violent, beautiful chaos of two spiral galaxies entwined in a gravitational dance, their structures stretched into long, luminous tails of ejected stars, while at their centers a firestorm of new star birth erupts. The sheer scale of the energy would be humbling, a continuous, silent fireworks display of supernova, each one a sun ending its life to seed the future. It would be a scene of both terrible destruction and glorious creation, all happening at once. This is where I'm incredibly curious to hear what you think. Does that vision match what you imagined? What questions does it spark for you? Do you see it as a violent, chaotic process, or does it feel more like a natural, rhythmic cycle of cosmic renewal? Maybe you have a completely different metaphor for what backwards aging might look like, perhaps a galactic fountain of youth or a celestial phoenix rising from its own ashes. Your perspective is a vital part of this exploration. The conversation about our universe shouldn't happen just in research papers and observatories. It belongs to all of us who look up and feel that innate pull of curiosity. So please share your thoughts, your wildest ideas, and your most pressing questions in the comments below. Every time you share, you're not just leaving a message, you're helping to build a truly special community of cosmic wanderers. We learn from each other, we inspire each other to look deeper, and together we get to unravel the universe's deepest mysteries, one conversation at a time. So to bring it all together, the universe has gifted galaxies with a few spectacular ways to hit the reset button on their aging process. First and foremost, we have the grand, violent drama of galactic mergers. When two galaxies are drawn together by gravity, their collision is far more creative than destructive. It acts like a colossal blender, violently mixing their gas reservoirs and driving immense amounts of raw material inward. This compression triggers a firestorm of new star birth, flooding the system with brilliant blue stars that completely overwhelm the light of the older, redder population. It's a cosmic-scale shock to the system, a sudden and dramatic infusion of youth that makes the galaxy appear millions of years younger almost overnight. But not all rejuvenation requires such a cataclysmic event. A more gentle, sustained method comes from cold flow accretion. Here, a galaxy can siphon fresh, pristine hydrogen gas directly from the cosmic web, those vast, invisible rivers of dark matter that structure the universe. This is a quiet, continuous top-up of star-making fuel. Unlike the violent compression of a merger, this process is like a steady intravenous drip of vitality, allowing a galaxy to sustain a low level of star formation for billions of years, effectively resisting the reddening fade to old age that affects so many others. It's a testament to the fact that a galaxy's environment is a constant source of potential renewal. And then we have the fascinating internal rhythms, the cycles of quenching and rejuvenation governed by a galaxy's own inhabitants. Here, the supermassive black hole at the galactic center plays a paradoxical dual role. In its active phase, it can blast out immense jets of energy that heat up or blow away gas, effectively quenching star formation and forcing the galaxy into a dormant, red and dead state. But then, when that activity subsides, the same black hole can indirectly trigger rebirth. Its milder outbursts can compress nearby gas clouds, or in the ensuing quiet, gas can cool and fall back in, reigniting star formation in a powerful burst. This creates a kind of galactic heartbeat, long periods of quiescence punctuated by brilliant flashes of youthful activity. What's truly remarkable is how these mechanisms all underscore one central, profound idea. A galaxy's age is not a fixed date. It is a fluctuating state, a snapshot of its current balance between resource intake and energy output. This is not time literally running backwards. It is the universe demonstrating that evolution is not a simple, one-way street. Time on these grand scales reveals itself to be flexible and responsive. It is a dimension deeply intertwined with a system's environment, its interactions, and its internal dynamics. By decoding these key mechanisms, the violent mergers, the gentle accretion, and the cyclical feedback, we gain so much more than just an understanding of why some galaxies look young. We acquire the tools to read a galaxy's entire history written in its light, to predict its future, and to fundamentally appreciate that the cosmos is a place of dynamic, ongoing change, where endings are often just new beginnings in disguise. So where does this leave our fundamental understanding of time? If we step back from the specific mechanics of mergers and gas flows, the overarching message from these cosmic rebels is nothing short of revolutionary. It tells us that time, on the grandest scales, is not the rigid, universal metronome we often assume it to be. Our everyday experience conditions us to believe in time's arrow, a one-way flow from past to future that never wavers. But the universe, in its magnificent complexity, operates on a different principle. Here, time reveals itself as a flexible, almost fluid dimension, its apparent flow shaped and molded by the dominant forces at play, the relentless pull of gravity, the distribution of matter, and the transfer of energy. This doesn't mean the laws of physics are broken, far from it. It means our appreciation of them must deepen. The same fundamental principles that govern a falling apple or the orbit of a planet also allow for these breathtaking exceptions. Gravity doesn't just make things fall, it orchestrates the majestic, slow-motion dance of galaxies, pulling them together to create conditions where time's signature can be locally rewritten. Matter and energy are not passive ingredients, they are active players in a dynamic system, constantly exchanging roles to fuel cycles of death and rebirth. This discovery doesn't undermine our scientific models, it elevates them, revealing a universe far more nuanced, creative, and wondrous than any simplistic model could ever predict. This realization should fill us with a profound sense of humility and awe. For centuries, we have tried to box the cosmos into our human-scale understanding, to make it fit neatly into our concepts of linear progression and irreversible decay. But the universe continually reminds us that it is grander, stranger, and more imaginative than we are. The phenomenon of backwards aging is a powerful lesson in intellectual humility. It is a cosmic check on our arrogance, a demonstration that no matter how much we learn, there will always be deeper layers of mystery to uncover, more astonishing phenomena that force us to rethink our most basic assumptions. It invites us to remain perpetual students of the cosmos, always curious, always questioning, and always open to having our minds expanded by the next great discovery. And so, as our journey through these cosmic mysteries draws to a close, we are left not with a neat and tidy conclusion, but with a far more valuable prize, a transformed perspective. We began by looking up at a familiar night sky, but we end by peering into a universe that is fundamentally more dynamic, more creative, and far more surprising than we could have ever imagined. These backwards aging galaxies are more than just astronomical oddities. They are profound teachers. They have shown us that time is not a rigid, linear path, but a rich tapestry woven from gravity, matter, and energy, a tapestry that can, in certain magnificent circumstances, fold back upon itself to create patterns of renewal and rebirth. This revelation stretches far beyond the boundaries of astrophysics, touching the very core of how we understand existence itself. It challenges the philosophers' long-held debates about time's arrow, offering tangible evidence that the flow from order to disorder is not an absolute dictator but a statistical tendency, one that allows for spectacular local exceptions. It invites the artist to visualize the impossible and encourages all of us to reconsider the stories we tell ourselves about endings and beginnings. Most importantly, these galactic rebels are a powerful testament to the spirit of scientific discovery. They remind us that the universe is under no obligation to conform to our expectations. Every time we think we have it all figured out, the cosmos has a wonderful habit of presenting us with a new puzzle, a fresh anomaly that forces us to question, to rethink, and to explore even deeper. This endless cycle of question and discovery is what makes science such a thrilling human endeavor. It is a conversation with the universe, one that requires humility, curiosity, and the courage to admit that we still have so much more to learn. If this exploration has sparked a sense of wonder in you, if it's made you see the night sky with a little more awe and a few more questions, then I invite you to join this ongoing conversation. Your curiosity is the most important tool we have. If you enjoyed this deep dive into the cosmos, liking this video and subscribing to the channel truly helps make more content like this possible. It allows us to continue unraveling the wonders of space, from the mysteries of black holes to the search for life beyond Earth. Thank you so much for watching, for wondering, and for embarking on this incredible journey through time and space. Never forget that the greatest discoveries often begin with a simple, courageous act, looking up at the stars and daring to ask, what if? The universe's grandest secrets are not hidden away. They are waiting patiently in the dark, just beyond the glow of our streetlights, for anyone willing to gaze into the depths and dream.